All right, so now we're talking about intermolecular forces. When two molecules come into close proximity, they may interact. And they would be experiencing some type of intermolecular force. Prefix inter means between. So an intermolecular force is a force between molecules. So we're not talking about a chemical bond here. We're talking about how one molecule affects the molecule next to it. The first type of intermolecular force is called the London dispersion force. These are the weakest of all the molecular forces, the intermolecular forces. And all molecules experience this force at some time or another. London dispersion forces occur when electrons and their normal orbits all end up on the same side of an atom momentarily. It happens especially with larger atoms and larger molecules. There's all of these electrons moving around, and there's just a chance that at any point in time, a lot of them could be more on one side than the other. For a very short instant, the uneven distribution creates a partially negative region and a partially positive region. In another instant, the electrons are evenly distributed again, and the London dispersion force is gone. London dispersion forces have a significant effect on large molecules. And this is really going to be affecting their boiling points. It explains why very heavy molecules tend to be liquids rather than gases. So the first one that we'll look at, let's talk about bromine. So bromine, it's one of our 7 diatomic molecules. This is what it looks like. Bromine covalently bonded to another bromine. And if we were just talking about your typical Lewis structure drawing, this is what it would look like. And you don't really need to draw it. Here's the covalent bond. But that's not really what I'm worried about right now. Let me move this over a little bit. Here's my 2 bromines. And bromines are pretty large atoms. Each of these is going to have 35 electrons, which is getting up there in number to the point where it's big enough that they start to not always behave according to the rules. And so I'm not going to count these. I'm just going to put a bunch of dots here representing all of the electrons in their normal orbits. And I'm not going to count them, but I'm going to say that's 35 right there. And then this other bromine, here's all the electrons in their normal orbits. And they look overall pretty well evenly distributed. They look pretty much equal to. So we're going to say they're equal. We're going to say they're distributed very evenly. Sometimes you get this instance where here's my bromine molecule, and this London dispersion force happens when a lot of the electrons tend to go to one side more than the other, and it just happens for a second. So here's my next instance, and look at this bromine atom. So here's the nucleus, and all or most of its electrons just happen to be all on this side. It's kind of lopsided right now. And maybe the same thing with the other one. They're just kind of all on one side more than we would expect. Get rid of a couple for clarity. Here we go. And so what we end up with is this partially negative area. Remember, electrons are negative, so this side of this atom is going to be partially negative. And there is a symbol that means partial. Here it is, partially negative. And this other side of this bromine atom is partially positive. Same thing with this one. We have a partially negative and a partially positive side. It's an interesting effect because if you look at a periodic table that's in color, like the one on the wall in our classroom, bromine's atomic symbol is blue. Most of the atomic symbols are black. A couple of them are red. Bromine is one of two that has a blue symbol. And that's because at room temperature it's a liquid. And it's because of this London dispersion force. These atoms are so big that they tend to become unevenly distributed. And when one of these bromine molecules finds another one nearby that also is experiencing this London force, they kind of pull each other together. And the closer that molecules come together, the more likely that this substance is going to be a liquid. And so that's what's happening here. It's finding a second Br2 and they're pulling each other together. There's another type of intermolecular force, and this one is called a dipole-dipole. This force occurs between polar molecules, and they're relatively strong. They're about 1% as strong as a covalent bond. But a covalent bond is a real chemical bond. This is just intermolecular force. These are two molecules that are influencing each other. So these forces occur when we have a partially positive end of one molecule interacting with a partially negative end of another molecule. In order to experience the dipole-dipole force, molecules need to be very close together, as in they need to be in the liquid state and not the gas state. So let's look at this molecule, unusual, ICl, so one iodine and one chlorine. And if you were to look at the bond between them, you have an iodine with an electronegativity of 2.5 and a chlorine with an electronegativity of 3. And so the difference is 0.5, which means that this bond is polar, a little bit polar. So when you get a bunch of these, so here is one of them, and let's say here's another one, and here's another one, and here's another one. So we've got 5 of these molecules, and they're all in pretty close proximity, and they're polar. So the chlorine is more electronegative, which means it's going to be the partially negative side, and the iodine is going to be partially positive. And so looking at this one first, I have my positive and negative ends. Partially negative end of this molecule is going to interact with the partially positive end of this one next to it. Same thing. The partially negative end here is going to interact with the iodine of this molecule. And this iodine is going to interact with the chlorine of the next one. And this chlorine with the iodine of the next. And we just end up creating all of these intermolecular forces, because these dotted lines are not a chemical bond, but they are places where this molecule and this molecule are influencing each other. This one is influencing this one, and so on.